How to find local extrema, so maxima and minima, of a multivariable function. In the vector field gradient picture, it's pretty clear. We have to follow the flow lines, the direction of the gradient, until we reach a point where we can't go any further. So this is a point where all the arrows point to. That will be a maximum. Or if we change direction of all arrows and consider minus the gradient, then it will be a minimum. But how to do this computationally? Instead, we realize that at a maximum or minimum, the tangent plane is parallel to the xy plane. That is, all partial derivatives are zero. In one dimensions, the corresponding criterion is the same, you know. The first derivative at extreme points is zero. But this was not enough. A sufficient condition for a point to be a local extremum is that the first derivative is zero, but the second is not zero. In the higher dimensional case, we have the same situation. There can be points with tangent planes parallel to the xy plane that are not maxima or minima. Saddle points are such an example. The derivatives are all zero, but there are directions where the function has positive, respectively negative curvature. In x direction the function goes up, in y direction it goes down. A sufficient condition for a point to be an extremum is that the directional derivatives of this point all have the same sign. Positive for minima, negative for maxima. We get this at once if we compute a matrix that is the higher dimensional equivalent to the second derivative and look at its eigenvalues. This matrix is called the Hessian. Its entries are obtained by twice differentiating, taking two partial derivatives one after the other. Second derivatives tell us how much the change of a function changes. Think of acceleration. Here we have, for example, the second matrix entry, del 2f by del x1 del x2. This describes how much the x2 component of the gradient changes if moving into x1 direction. It doesn't matter in which order the derivatives are taken. That is, the x2 component of the gradient changes in x1 direction just as the x1 component changes if moving in x2 direction. This is the Hessian matrix is symmetric. On the next page we see an example, but first let's go through the whole process of finding extrema. Now, a symmetric matrix can be positive or negative definite, which is all eigenvalues of the matrix are greater than zero or smaller than zero. The matrix is indefinite if it has both positive and negative eigenvalues. Quick reminder from linear algebra. A n times n matrix corresponds to a linear function from Rn to Rn. Its eigenvectors give the directions in which the function maps a vector onto a multiple of itself. And the factors, which give the value of stretching or shrinking in the eigendirections, are the eigenvalues. For the Hessian matrix, the sign of the eigenvalues tells us the curvature of the original function in the direction of its highest and lowest ascent. So if we have a positive definite Hessian in a point, we know that the point is a minimum. Negative definite is a maximum, and indefinite Hessian matrix tells us that we have found a saddle point. If there is a zero eigenvalue, this means that in our point might be a maximum or a minimum, but the point could also sit on a plateau or a ridge. In this case, the test doesn't conclude anything. Let's take a break from formulas for a moment and look at this vector field. How do the arrows change if we move in x direction? You see that the arrowheads of arrows in one horizontal line are all in the same y value, so no change in this component if moving in x direction. The arrows become larger though. There's a change in the first component of the vectors, namely by a factor of 2. Same in y direction. If we move in y direction on the xy plane, the first coordinate of the vectors don't change, but the second does, namely by a factor of -2. Now let's go back to computations. This vector field is a gradient g equal 2x minus 2y of our saddle given by the function f x squared minus y squared. The matrix is the Hessian matrix of F. We get its entries as introduced on the last slide. The first is 2, which is F differentiated twice in x direction, and this is what we just saw. The gradient changes with a factor of 2 if we move in x direction. Same for the other entries. Perhaps it's good to stop the video for a moment and check that you can follow how the Hessian was computed. The functions g1 and g2 denote the first and second entry of the gradient, the two coordinate functions of g. Let's not forget how we ended up here. We actually wanted to determine maxima or minima, extreme points of our function f. So necessary criterion, first derivative, so the gradient should be 0 in a point, Well, g is 0 for the point 0, 0 for the origin, because 2 times 0 and minus 2 times 0 is exactly 0, 0. Okay, is the origin really a maximum or a minimum? Well, we know already it's not, and that is what we see in the Hessian. What are the eigenvalues of our matrix? Well, in this case, it's really easy to see because they're just the entries of the diagonal. It's 2 and minus 2. So we have one eigenvalue that is positive and one eigenvalue that is negative, so we detected a saddle point. Now, if you completely forget that the function g was a gradient, it's just an example of a function from Rn to Rn, where here n equals 2. And the matrix is the first derivative of the function. The first derivative of a function from Rn to Rn should be a n times n matrix. Its entries are the n partial derivatives of the n coordinate functions. So you already know how to differentiate functions from Rn to Rn. The matrix is called the Jacobian matrix of G. Actually, there's absolutely no reason to only restrict to functions from Rn to Rn. We also know how to get derivatives for functions from Rn to Rm. Namely, their Jacobian matrices have the gradients of each component function in the rows. Here it's written out. The function that gives g1, the function that gives the first component of the image, differentiated with respect to each coordinate, is written in the first line. The partial derivatives for the second component function of g that gives the second component of the image, written in the second line, and so on. So that's in the most general case the first derivative of a function. One slide on Extrema under constraints, which is not exam relevant, and I only want to tell you what the concept is because we're skipping that. So look at the function f of xy, whose graph is this purple surface, and we constrain it to the points xy that are given as the function g of xy equals c. So that is a parameterization of the red path. Now, where's this red path maximal? That is finding an extremum of the function f under the constraint we only can walk along the red path. The condition for having a maximum here is that the tangent along our path will be tangent to a level set of our function f. Sure, if I'm not going further up, if I'm not going down, if I just change from up to down, my tangent should be along a level set. Or, seeing it from the orthogonal perspective, the gradient along my path should be parallel, so a multiple of the gradient in this point for my function f. This gives us a necessary condition for these extrema under constraints. We search for those points whose g gradients are a multiple of the f gradients. And this multiple is what's called the Lagrange multiplier. So much of linear approximation of a function. Well, this is what differentiation is doing. There was one more thing we used that for in the one-dimensional case, namely for the Taylor approximation, which was approximating a function by a polynomial that the first derivative attached to a function value, and then the second derivative and the third in this one point where we approximate about. So if that point is x0, then in the more dimensional case we do the analog. We start with f of x0 to get the height right, and then we attach x minus x0 times the first derivative analog, which is the gradient. There's a t written at the vector x minus x0 because we have to take the transponent to have the dimensions right and be able to take the dot product of the vector with the gradient. And then the third, there you see the second derivative analog, namely the Hessian matrix of f in the point x0. The factor a half shows up again, and instead of x minus x0 square, we multiply the Hessian from both sides. If we stop here, we had a second order approximation of our function. Or we can go on, but I don't think you will ever do that by hand. This is for you to understand. I'm not going to ask you to write such a thing out on the exam. A warning at the end. The length, area or volume of an object in the domain is usually different from that of its image. It is clear in the picture that the image of the green or purple squares have areas that are different from that of the squares in the xy plane. And not even that, although the squares in the domain have both the same area, namely 1 here, The images have different areas. This might not be surprising, but we must not forget this when using functions for transforming coordinates. This is for the content of week 10.